Question 6 continues. The smoke alarm would not work with a radiation source that emits beta or gamma radiation. Explain why. Because they would go right through smoke as if it wasn't even there. 2 marks. Really? Alright, beta radiation would go right through smoke as if it wasn't even there. Gamma radiation would go right through smoke as if it wasn't even there. Is that 2 marks worth? Smoke alarm changes with time. Of course it does. Because the definition of a half-life is the time it takes for half the things to decay, after which there are half as many, so with them each one just as likely to decay in any given length of time, there's half as much radiation coming out. Let me guess, that's the next question. 80 counts per second. Because you want the thing to stay reliable for years and not give a false alarm. Otherwise people are going to start ignoring smoke alarms. A radiation detector over a person's leg. That's cool. Wearing a watch and a ring. That's a luminous watch, it could be a problem. Ideal properties of a radioactive source in medical diagnosis. Well, for a start, polonium-210 is a bad choice because it's poisonous. Same applies to ricin, botulinum toxin, lead, mercury, quite a lot of other things. Has to be water soluble because we're water-based life forms. It better be giving off beta or gamma radiation because it's got a layer of skin and a whole lot of air to get through to reach that detector. And you want something with a short half-life because it's going to you want it to give off enough energy to be detected in the time that that patient is there, while giving off fairly little energy in total, over its first 20 half-lives. If its half-life is measured in thousands of years, it would have to be an incredible total dose for the first 30 seconds or whatever to be measurable. And it has to be something that would enter the bloodstream, but that's more of a biology question than a physics one. And then something that will be eliminated from it rather than accumulate in the bones, maybe. A student investigated how the pressure exerted by a gas varied with the volume of the gas. A pump was used to compress the gas in a tube, which is pumping gas from somewhere else through the pressure gauge into the tube. Now, as the volume of the gas decreases. I'm sorry, but how? Oh. Right, it's pumping liquid into the tube, oil probably, something incompressible, which water nearly is. This will be the top of the liquid. The gas is caught in this space above it, the upper part of the tube. So as the liquid is pumped in, it's compressing the gas more and more. Assuming the gas isn't just dissolving in the liquid. The student only recorded one set of results because the student was short of time and had to get to a jiu-jitsu lesson. Give 2 reasons why taking repeat readings could provide more accurate data. Well, temperature changes between readings. You might make parallax errors in reading because your eye isn't quite level with the surface meniscus each time. There we go, that's 2. Position of the student's eye when taking volume measurements. That's correct. Might be a little close, but it's correct. Parallax error, I already mentioned that. Because you'd be looking at an angle and you would see one of these markings or one of these markings, not the one that's actually level with that. If the gas is compressed too quickly, the temperature of the gas increases. This is not correct. When the gas is compressed, the temperature of the gas increases. So the faster it is compressed, the hotter it's going to get. This is ideal gas law for a constant mass of gas. Pressure times temperature over volume is constant, I think. Well, pressure times volume at the same mass and temperature is a constant. Pressure increases with temperature, so they can't both be on the same side. Number of moles times temperature divided by volume divided by pressure times temperature is constant. For a fixed mass and volume, pressure is proportional to temperature, which is one of the simplified versions, ought to be good enough. Question 7 continues on the next page. Pressure is 1.6 times 10 to the 5 pascals. Volume is 9 cubic centimeters. When it was 1.8 times 10 to the 5 pascals, temperature of the gas was constant. Yes, perfectly constant, because that can happen in GCSE Physics. It doesn't happen at universities, unless you use some very expensive equipment. Right. Well, for fixed mass and temperature, pressure is inversely proportional to volume. So pressure is down to 1.6 from 1.8 if we're letting the stuff back out, or this was earlier and it's gone from 1.6 to 1.8 as we pump the liquid in. The volume will have decreased in the same proportion as the pressure increased if we're pumping liquid in, or it will have increased in the same proportion as the pressure decreased if we're letting liquid out. So the answer is 1.6. 9 times 1.6 over 1.8, which is 8 cubic centimeters. They even provide the units. You can't lose marks for forgetting to provide the units. Figure 14 shows a person using a bicycle pump to inflate a tyre. I mean, I joke about how old the bicycle is with the basket on the front and the mottled paintwork here on the forks. How old is that bike pump? And who the heck cycles in flip-flops? The internal energy of the air increases as the tyre is inflated. Explain why. Internal energy of the air, that's an interesting way of phrasing it. Because you're using energy to force air into there and the energy can't get back out. What's that? Fission. Now, to me this is an environment question, maybe geography. I mean, it doesn't cause earthquakes, it doesn't pump poisons into the groundwater by accident. In the process of pumping poisonous stuff into the ground rocks to crack them open to release the gas. It doesn't contribute to global warming, and it releases less radiation into the air because the shale gas is radioactive. One fuel used in nuclear power stations, uranium-235, which is enriched from uranium, which is extracted from yellow cake ore. Describe the process of nuclear fission. 4 marks. A nucleus breaks into smaller pieces, releasing energy. That's pretty much it. If we're talking uranium-235, you could go into details about the fission products breaking down further. I mean, it's been a while. Getting a gas out of it, I'm sure. You get unstable isotopes of other elements, and it gives off neutrons which collide with other nuclei, and if they stick to them rather than hurtling past or bouncing off, trigger more nuclear fission. So you get a chain reaction. Figure 15 shows a coffee machine, which is probably not directly nuclear powered. Using an electric element to heat water. You do not surprise me. This paper was not sponsored by DeLonghi. Coffee machine has a metal case. Why would it be dangerous for the live wire of the electric cable to touch the metal case? Because that would allow mains electric current to flow through the case to whatever poor sod touched the machine, and through that person's body to the ground in general, massively stimulating nerves around everything on the way, including the heart, causing cardiac arrhythmia or even cardiac arrest. Also, because the electric current flowing from the case of it to whatever it touches, which could be, through a spillage of impure water on the counter to the sink, would generate heat and could cause a fire. There's only one mark for this. Power output is 2.53 kilowatts. The main potential difference is 230 volts. Calculate the current. Power equals potential difference times current. Therefore current equals power divided by potential difference. 2530 watts divided by 230 volts equals 11 amps. Coffee machine heats water from 20 to 90. The power output of the coffee machine is still 2.53 kilowatts. The specific heat capacity of water is 4,200 joules per kilogram degree C. Close enough. Calculate the mass of water that the coffee machine can heat in 14 seconds. 4 megatons. You didn't say that it can heat from 20 to 90, did you? Just that it can heat. Anyway, in 14 seconds, with a power output of 2,530 watts, it is outputting 35,420 joules. Dividing that by 4,200 joules per kilogram degree C means it is enough for 8.43 recurring kilogram degrees C. But we want to heat it by, open bracket 90 minus 20 close bracket, also known as 70 degrees C, not just 1. So if we divide that by 70, we find that it is 0.120476 kilogram times 70 kilogram degrees C, or 0.204761 kilograms times 70 degrees C. So the answer is 0.1205 to 4 significant figures kilograms, which is not much. It's a little shy of being 5 UK pub measures, or 1 of spirit, 1 wine measure. Figure 16 shows a wind turbine. Well, so much for your cup of coffee. (2.3 times 10 to the 4 cubic meters of air, so that's 23,000, passes the blades each second. The density of air is 1.2 kilograms per cubic meter at sea level. But this is GCSE Physics. They don't bother specifying that. Just treat it as that number everywhere all the time, Calculate the mass of air passing the blades per second. 3 marks. Density is mass divided by volume, therefore mass is density times volume, which is 1.2 times 2.3 times 4 10 to the x equals 27.6 tons. Oh, they want kilograms. 27,600 kilograms. The power output of the turbine is directly proportional to the kinetic energy of the air passing the blades each second. And the wind speed is halved. They're going to go with the approximation that kinetic energy is a half mv squared, which for, terrestrial wind speeds that wouldn't vaporise a wind turbine. Reasonable approximation to use. Half mv squared, if you halve v, you get a quarter of the v squared, so you get a quarter of the kinetic energy per unit mass. Right? But it depends on the energy they're passing the blades each second. If you've got half the wind speed, there's only half the mass passing the blades per second, so you get 1/8 the power output. $388 kilowatts, 13,800. Assume that the process is 100% efficient. Yes, because you have to do that for this simple little question. And oh boy, do we wish they were. At a different wind speed. Right. We still have 1.2 kilograms per cubic meter. Not that anyone cares. 388 kilowatts. Well, we know that 13,800 kilograms times a half times v squared equals 388,000 joules, because a watt is just 1 joule per second. So if we divide 388,000 by a half, 776,000, and by 13,800, 56.23, that's v squared, and the square root of that, 7.49879, also known as 7.5 to two significant figures, is the speed of the air in meters per second. That's a reasonable airspeed. That's, so I can tell you exactly. (16.77432 miles per hour). That's a reasonable airspeed. End of questions. We have completed this paper. Right. Close that, and I can go full screen on this. Lumbosacral transition vertebrae. That's what you get when you put in funny search terms. And go back to where I was, which is the same paper. And, oh yeah. Switch to here. Close that tab. And grab the marking scheme. And see how we did. Can we remember our answers? Well, no. Blah, blah, blah. Blah, 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 blah. Blah-de-blah, blah, 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 blah. Blah. Use of chemical formula. This is supposed to be a physics paper. Come on! Transfer of electrons from the carpet to the student. Mention of positive charge moving negates both marks. But yes, transfer of electrons from the carpet to the student, like I said. 3 arrows perpendicular to the sphere's surface with all arrows directed inward and distributed evenly around the sphere. So the tetrahedron is actually correct, but they probably want the square. But I don't know, if the person marking it's smart, they'd probably give you the points either way. The difference between the student and the tap. Yes. Which causes electrons charges to transfer from the student, or which causes electrons charges to transfer to the tap, which earths the charge. I do believe I said that. Allow the tap is earthed, which I also said. So, okay. Carpet / copper has a low resistance. Carpet as a conductor is not the answer. Copper is a conductor. I mean, we had carpet before and it wasn't working this way. Yes. Yep, said that too. Count rate, 819 over 60 equals 13.65. Corrected count rate is 13.35. Yes, they did want that. 2 marks if you don't correct it. Or you could convert the 30 per second. Wait, an answer of 801 per second scores 2 marks. If you converted the background radiation to per minute, it would have gone from 0.3 to 18. Subtract that from 819, you get 801. But this should say per minute, not per second, for 2 marks. There we go. It says per minute there. This says per second. So the marking scheme's wrong. Activity, 1250 times 180 is 205,000 becquerels. Yeah, that simple. Yearly dose. Multiply that by year, which is a heck of a lot less than 100 millisieverts. Oh, you don't even need to multiply it by a life expectancy of 80 years. Just per year is good enough. I went a little too far. That's it. The only one they like is that it lets people compare risk to the dose from eating a banana. That's a pretty lame answer. Voltmeter in parallel with wire, ammeter in series with wire. I said that. Right, 1 to 2 marks, even if the method would not lead to a valid outcome. Up to 6 marks if it actually would and was properly explained. So, to do it properly, you measure the length of the piece of the wire along which you're passing the current, and you vary it. So you take multiple measures. Measure the current, measure the potential difference, repeat the readings, just take lots of readings, repeat the readings, apparently they like it when you do that. Calculate the resistance at each length, which is resistance equals potential difference over current, plot a graph of resistance against length. Hazard, high current may cause wire to melt overheat or cause burns to skin. Use low currents. Yeah, I think I got most of that. Temperature of the wire would not change. I said, didn't I, that the answer they want is that the temperature of the wire would not change, because the temperature was the issue. And the accuracy will be higher because the resolution of length measurement will be higher. Got that. Chemical equal to. Yes, chemical energy in the student's body, as long as the work he's doing is equal to the air resistance, because his bicycle is 100% efficient. Yes. Power is work done over time. Yeah. 360,000 joules. Yep. Any answer that rounds to 15.8% scores 2 marks. Our change in speed between 1.2 and 1.5 meters per second. What? What the heck was question 0.4? 04.4. 11 minus 9.5 equals 1.5. That's the change in speed. This was the cyclist's speed changes. How much work is he doing? Times 100, 15.8%. I don't remember what the question was for this one. I'm sorry. Maximum speed is lower because maximum power output of cyclist is constant, but additional work is done against gravity. Gravitational potential energy of cyclist is increased. Do not accept additional work done against friction, because the only friction is the friction between the tyres and the road, and that's what you're using to propel yourself forwards. This bicycle has no friction in its bearings, and anyway, going up a slope wouldn't change that friction. Maximum force on pedals is constant. Maximum average force over one full revolution on the pedals is constant. Potential difference, temperature. Again, I forget the question. Current increases when the potential difference increases. Oh yeah, this was the light bulb filament, wasn't it? Increases with increasing temperature. Which causes the temperature of the filament increase, so the resistance increases. Yeah. Higher proportion percentage of the total power energy input is usefully transferred. Higher useful power divided by energy output, same total power divided by energy output. Yeah, because the light output is the useful power output, and heat output is wasted power output. And they don't like wasted, they like it to be part of total. Oh well. Potential difference increases, current decreases. Something about the variable resistor in the lighting circuit. 1000 ohms, because potential difference is shared in proportion to the resistance. Yes, it is 1/3 of the total resistance because it is 1/3 of the total voltage. 7,000 ohms total. Therefore, the current across the particular component, 1.7 times 10⁻3, or 1.7 milliamps, or 0.0017 amps. Only they don't like milliamps because they put in amps as the units. 4 marks if you got that answer, which I did. Who's next? Smoke absorbs / stops alpha radiation. Yep, alpha radiation is not very penetrating, or does not penetrate skin, or does not travel very far in air. Beta and gamma radiation will penetrate smoke, and it wouldn't affect the... Oh, you have to put in that, yes, it wouldn't be detected. Good grief. A long half-life means the count rate is approximately constant. A short half-life means the count rate decreases quickly. Activity of sources. Yeah, so you don't need to keep retuning the thing for how much smoke it detects. Until 1.3 half-lives. I think that's a shit answer. The answer they wanted was that until 1.3 half-lives, the count rate is above 80 per second. Well, that's just reading off the graph. That's not explaining what's great about having 1.3 half-lives being a long time. What's this? Short half-life. Because there's less total energy, less damage. Why does it... They want you to say that a short half-life means it will do less damage. Do they want it to explain why? Low ionizing power. Beta and gamma are actually less ionizing than alpha, which means less damage. Yes. Highly penetrating, which means beta, gamma, not alpha. Means it can be detected outside the body. Yes. Emits gamma radiation. And he just says that without explaining that makes it highly penetrating and low ionizing power. But yeah, you want something that'll give off all its energy very quickly, well, not super rapidly, but quickly, and be detected outside the body. Next part.